Welcome everybody. We're going to get started here. It's a busy agenda for the Construction Engineer Bridge Overview. We fondly call it CEBO for short. And this is a 3-day class. And so we'll be going over here in the next 15 minutes or so, a little welcome and introduction. Obviously this is online. It's via the Zoom platform. I just sent a message off to Erica. It looks like probably are the attendees able to speak, or do I have to unmute them? So one of the questions that I have, Erica.
Yeah, if they want to speak or have interaction, if they raise their hand, then you'll know who wants to speak, and then you can give them access to talk. Okay,
but I have a list of it goes beyond the page, so I will try to monitor it. But this should go well. We've done the 2-week bridge construction inspection class online. It goes pretty good. Obviously, it's with training, it's nice to have the personal interaction. So we're unable to get that, but we would like to be able to have participation as we go. We do have a couple of group exercises, so we're gonna have to figure out how we can more easily get people to be able to chime in with voice. There is a question and answer box, so up at the top of your screen. I'm not sure if you're able to see my cursor, but if you move your cursor up to the top of the screen, there's a little panel that comes up. There's a mute button, there's a video button, a participants panel. So if you click on participants, you can see who all is in the class, Q&A, and then I think you probably have a chat. The unfortunate thing, I don't have the chat box when I'm presenting. So somebody's gonna have to help me out to be able to do that. Mark, maybe I'll move you into the co-host here at some point as well. Maybe I should do that just so there's somebody else that's able to monitor and be able to help out with questions. So, Mark, I'm going to promote to panelists, so now you should be able to help out. Okay, so there's going to be a few little things as we work through the Zoom meeting here, but again, hopefully it can be interactive. Hopefully you all get an excellent overview of bridge construction and the things associated with it. So there's a lot to cover, a lot of information. We'll go over the agenda here in a couple of slides, but without further ado, we will get moving. This course is being recorded, and it's being recorded for the purpose of giving other people the opportunity in training to be able to get on and see the kind of things that you're able to see here during the class. So as a part of that, you are part of this. And the Tennyson warning, I'm going to read the whole thing. You guys have it on your PowerPoints as well. As part of its business activities related to training and development, Lake Superior College and Minnesota Department of Transportation will be recording this class, a 3-day CEBO class via Zoom, including chat and questions and answers for the MnDOT Office of Workforce Development and the Bridge Office for viewing by the general public because it will be posted on MnDOT's YouTube page and on MnDOT's Bridge Office for interested parties. So if a co-host, so that would be myself or others, has enabled your camera during the session, the recording may include your image, and it may also include your voice. You are not required to allow Lake Superior College and MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, simply turn off your camera. So the recording will be accessible to anyone and anyone authorized by law. So just a general warning there of what we are planning to do with this class. The course materials, you were sent a link to all of these things. We are going to be using a sample plan. It's bridge number 27138, and it's a pre-stressed beam bridge. It's 2 spans. kind of a basic bridge, but it has a lot of things that we're going to be talking about in the various components. So if you haven't already, make sure you download that, whether electronically or print it out, however you want to use it. It really doesn't matter either way, but just be able to get to it so that you can utilize that as reference. There's also a proposal with the bridge special provisions that was provided. And then the course manual is actually a compilation of all of the PowerPoint slides that we will be presenting. There's going to be a lot of different presenters. We'll talk about that in a moment. But the PowerPoint slides are there. So you can follow along, you can make notes if it's electronically or if you've printed them out hard copy, however you want to do it. But those are available, and that's essentially what the course manual is. Some other useful items. We are going to be referring to the MnDOT Bridge Construction Manual. That is available online on the MnDOT website. You can get to that. And also the 2018 MnDOT standard specifications. So we're going to be going over in some detail a little bit later this afternoon about what the specs, how they're written, how they're developed, those kind of things. So very useful for you to have that. We're going to be referencing, various parts of the spec, and on page such and such, here's where you find this item. So it'll be good for you to have access to that. If you don't have it handy now, make sure you get that. So our agenda is 8 o'clock to 5 o'clock each day. So we'll start right at 8. Our agenda that we will show on the next slide shows us ending at about 4:30-ish each day, maybe a little bit later. But as can often happen in training, sometimes we start running a little bit long. So expect that we may go to 5 o'clock, depending on how the day is going. We have a half hour for lunch, and it's interactive. We want it to be interactive. So use the chat box or the voice. And then we do have some group exercises. Again, I'm unsure how this is going to work, if we're going to be able to make everybody able to talk, or if you're going to have to raise your hand and we select you. I'm not sure how that's going to work, but we certainly want participation. We have a couple what's called Mentimeter knowledge quizzes. They're a short little quiz. Nothing is graded here for this class. Right after this welcome, we're going to have our first one. It's going to be just to kind of gauge where the class sits and so forth. So the agenda, you have a copy of the agenda. You've been provided a copy of the agenda. So I'm not going to go over it in any great detail. But again, 8 to 5 each day, or even closer to 4:30. But we will be following this agenda. So the numbers there, like 2.01 is starting with bridge styles, a historical perspective. So you can find that presentation in your documents, and then so on and so forth. So tomorrow, in general, today we're going to spend the morning talking about some of the basic things about bridges, bridge design. What are some of the forces and stresses that we deal with in bridge construction? How do we counteract them? What are materials, that kind of stuff. Then we'll get into a little more detail with some of the foundations and get into OCIC comes on this afternoon, Kevin Kazabud, and we end up with painting and barriers. And then we go tomorrow with some foundation things, and the foundation thing gets fairly lengthy, and this is something that it's almost a full day when we do it in the 2-week course, but there'll be some good information there. Substructures, superstructures. We'll start to get into rehab a little bit tomorrow afternoon, and then Thursday we will finish that up. We'll get into some environmental kind of things, some approach panels, retaining walls, so on and so forth. So, and then we have a group lesson at the end of what do we do, a pier cap example and things like that. There'll be time for discussion at the end, some closing remarks, and then a post-test of what kind of information have you been able to gain from here. So a little bit about who is going to be instructing. My name is Paul Kivisto. I work with WSB right now. I was an employee with MnDOT for over 36 years, almost 37. And my timing for retirement was really something. I put my retirement papers in on a Friday, and that weekend the whole COVID thing started really falling apart. But I still decided to go through with it, and I'm now working, trying to be a part-time schedule with WSB, doing training, doing bridge engineering kind of stuff. So, but happy to be involved with this course. I really enjoy teaching and imparting knowledge to the folks that are starting out on bridges. So there's also a lot of people in the bridge construction unit. I'll be showing some of them here shortly. Office experts in everything from aesthetics to the structural steels to whatever. And then MnDOT subject matter experts from OCIC, from the concrete office, from environmental, that will be helping us out as well. So the MnDOT Bridge Construction Unit is staffed, headed by Ed Lutkin, Bridge Construction Maintenance Engineer. And then Paul Pilarski, you'll be hearing quite a bit from Paul through the course of the week here, of the 3 days. He's leading up the Bridge Construction Unit as well as the scoping. Mark Spafford is the engineering specialist, covering a lot of the special provisions, the spec book and things like that. Andy Fritz, engineering specialist, covering the whole state. He gets involved a lot with the piling and so forth. So you'll be meeting those guys as they move on, as we move on through these days. The regional construction engineers, important positions, and they help out all the MnDOT districts and the locals. So Nick Haltbeck is the North Region engineer. The Metro is divided into two. Nate Schutte has the western part of Metro. He's been on a mobility, but he's back into the role now. And then Ashley Grzybowski has the East Metro. And then Carl Gronval, the southern three districts, 6, 7, and 8. Great resources. It's a position that they deal a lot with the districts and so forth. So that's some of the staff that we have, but be familiar with these folks. They're great resources for things that you do. Typically, we try to go around and see who's who, but on account of time, we're not going to do that. But really, we know this is a class for people that haven't been around bridges a lot, and so we are cognizant of that. This class is sponsored by the MnDOT construction and the bridge offices. Mainly the bridge office put it together, but the construction office has been instrumental in putting together some of the presentations as well. And then in cooperation with Lake Superior College, who's done a great job of helping set this up and get it going. So thanks, Erica, for your work on all of that. So what's the class? We have had this class typically about every 2 to 3 years. It was last taught in 2018. And the resident engineers and OCIC have really felt that this is important to get you folks as kind of younger engineers up to speed on bridge related items. And so that's where part of this content comes in. Class is informal. Again, it's harder here with this Zoom to make it that everybody can participate, but we encourage you to participate. Ask, don't wonder. If you have a question, you've heard it a million times, somebody else has that same question. So don't worry about that. And obviously the best classes have a lot of student involvement, so we will try to institute that as best as we can. It is a bridge construction overview. It's not going to get into the detail like we do in the 2-week class. We're presenting many different topics, but the basis of bridge construction will be covered. It is intended for people that haven't done a ton of bridge stuff, so it's intended for rookies. Bear that in mind when doing the evaluation sheets. So our goal is to provide an overview of the practices and specifications and to review basic terminology and procedures. And obviously, whenever you take training, you get some great material. So that's a resource for you. Use it. the resources that we have in these PowerPoints can be used, but also the contacts with these regional bridge construction engineers are great. So we'll take you from the course manual. There'll be some references to the special provisions, to the standard spec book, and so forth. We'll use that plan for Bridge 27-138 to illustrate where the material usually is, and we'll take you into the specs to see what are some details that apply to this plan. So there's a lot of photos. Everything is essentially PowerPoints that we're going to be using. So go with that. Course evaluations at the end of each day. I'm going to try to remember, and Mark, Paul, maybe you can help remind to send out that link, but it's a 3-day class. The evaluations kind of talk about each of the subjects. So we're going to try to put it out every day. So please complete and make some constructive comments. Why? Because we do look at this. Even though this class is every 3 years, the last time we had it, we looked at those comments to see what kind of things should we shorten, add, take out, whatever. So it's good to have that. So be willing to do that. So there is, as I mentioned, that Mentimeter. It's a quiz. It's ungraded before and after the class. So just to see what do you know when you come in, what do you know when you leave. For you as a student, make these 3 days count. Ask questions. We know these online relationships are more difficult, but gain the contacts of these regional bridge construction engineers and others in the bridge office. And then think about, what is your goal? What do you want out of this training? On the bridge office website, there's this page that talks about who the folks are. We showed the pictures already, starting with Ed and Paul up at the top and the regional guys. So, there's the contacts that you need. Again, it's on the bridge office website. And just a picture of the plan front sheet. So with that, I'm unable to see a chat box, unable to see any questions, but does anybody have any other questions? Okay, now I need to, not sure here, but I think I'm, a new share. I gotta do a new share. And the next thing we are going to do, if I can find it here. I need to get to our Mentimeter. Sorry, I have too many things open. There we go. Okay, so I think you guys, Mark, you should be able to talk. Can you see now the Mentimeter?
Yes.
And I'm going to hit present. I'm going to give you guys about, say, 10 minutes till 8:30 to go through here. There's 20 questions, and just like you to get through all those questions. You should be able to go through from first to last. So I'm going to give 10 minutes. Mark, if you want to start it too, just make sure that you can get all the way through. It's like on the 2-week class, we had that case where they got through about 10 questions and it quit. Okay, moved over to 8:30 on my computer here. So we will go over this little quiz. So if you haven't finished, you can either keep on going or just listen with one ear and whatnot. But so the first question that I put on here is, how many years of bridge design or construction experience do you have? Just to kind of gauge what the makeup of the class is. And it's as we anticipated. It's most of the people here have no bridge experience, or maybe 1 year, and then a few in the 1 to 3 years. So that's exactly the kind of people I think that can benefit from this class. And then Mark probably skewed the curve. He's more than 10 years, but there's a few people with a little bit more experience, and that's well and good too. And we learn from each other. So but it's good. And when you are new to bridges, those of you who have no experience, 0 to 1, again, feel free to ask these questions. The stuff we're going to be throwing at you is going to come hard and fast. And if it gets overwhelming, feel free to raise that hand, and we can chat about it. Okay. So which MnDOT standard specification covers the majority of cast in place concrete bridge construction, placement and curing? So concrete, the key word here is concrete, and then also the placement and curing. And so the correct answer here is 2401, and we're going to be diving deep into 2401. And when you get a bridge project, you're going to know 2401 inside out and backwards. 2461 talks about structural concrete, but it talks more about how to make the structural concrete. What are the different grades? What are the admixtures? Some of that kind of stuff. So there's some curing things that get into that, but the majority of bridge curing is going to be in 2401. And so that was the intent of that spec. So 1517 talks about claims. 2402 talks about steel construction. We are going to be doing that. Nick, I believe, is the one that's talking about some of the steel. And 2452 is piling. So those are things that we will be going through. So again, as you move through the spec book and you start doing more on bridges, these are the kind of things that you will get really familiar with. What's 2401. In fact, you'll be able to pull out 2401.3 G2 and things like that. Okay, where in a typical bridge plan can you find basic criteria used for designing the bridge, including design code and methodology, live loads, and materials? So a lot of you have front sheet of the plans, which is the correct answer. That's basically, there's a box, and we'll be looking at it in a presentation or two of what that entails. And I think Ben is the one that's going to be talking about some of these kind of things. But typically that's where it's located, the design codes, the methodology. So a lot of you said scattered throughout the plans, and there might be some references, but it's really that front sheet of the plans. If you wanted to see what the operating rating is, what live load is used, that's where it would be. And those who said these items are not typically included in the plans, there is that box on the front. So we will be going in that. So what's the benefit of using load and resistance factor design, LRFD? So it's based on probability. That is true. It encourages use of redundant members and ductile materials. That's true. Ductile means it's not going to be quite so brittle. It considers variability in construction and field conditions. Yes, that's true too. But the correct is yes, all of those. So again, I believe it's Ben that's going to be talking about those later this morning. So deck pour sequences and construction sequences shown in the plans can be changed without contacting the engineer if the contractor signs off on it. And that is false. There is a reason that the plans, if a plan indicates something, yes, it's there for a reason. And if they change it, some things, even like the grade elevations, the construction elevations might change if you cast and make something, pour the concrete in span 1 and let it cure. Then when you pour span 2, it's going to deflect much differently than if it was non-composite. So we'll talk about some of those kind of things as well. So which of the following can be used to determine the capacity of a CIP pile? So that's cast in place pile is driven in the field. Select all that apply. So pile sounding method, that's just a term I invented. So that's not a term. MPF 12 formula. We will be talking about that, and Andy will go into that. That's the main formula that we use in the field now. It's a dynamic formula. And so the MPF 12 is one correct answer here. Allowable stress dynamic formula, we used to design and control things with what's called allowable stress methods, but we no longer do. So that LRFD question that was a couple of slides ago, that's some of the basis for some of this kind of stuff. Pile driving analyzer, yes, that's a tool that we now have to be able to analyze. As you're driving, you hook up gauges and then you can tell what the capacity is. WEEP is something that's used in the before the pile is ever driven. So it's something to qualify our pile hammers. And so that's not the correct answer, nor is LRFD. LRFD is used in a lot of things, but it is not what is used to control our piles. So the answers are these two, MPF 12 and pile driving analyzer. What is the typical curing period for a structural concrete deck? So this is in 2401, and there's a bunch of tables that we'll be talking about, but the correct answer is 7 days. So there are a lot of things are 72 hours, but a deck is 7 days. And then some of these other ones, 28 days, you may have heard about 28-day strength. Yes, that's when concrete cures, it gains strength pretty rapidly early, and then it kind of slows down. But we're really looking for what's called a 28-day strength, but that's not the cure. So the cure again is 7 days. So these longer ones are also incorrect. So 7 days is shown in 2401. So what is the most common type of rebar used in Minnesota bridges? Okay, so 40 KSI is an older material. That's in the terminology, KSI means, K means 1,000. So this is 40,000 pounds per square inch. Or in bridge land, we often use this KSI terminology. So the 40 is a lesser strength. We use 60 KSI is by far the most common rebar that we use. And uncoated rebar we will find is going to be in things that are not exposed to the air at all. So footings can have uncoated bar. So there is 60 KSI bar, uncoated bar, but the vast majority is going to be 60 KSI epoxy coated rebar. We are starting to use stainless steel rebar in bridge decks, but nobody selected that, and it's pretty, I wouldn't say rare, but it's only on the bigger type bridges. And then 75 KSI epoxy coated rebar doesn't get used much at all. But so the main one here is the 60 KSI bar. For an HP 12 by 53 pile, what does the 53 designate? Okay, so we have length of pile in feet. No, that's not what it is. Was the HP 12 by 53 is the sectional properties of the pile. And so the weight of the pile in pounds per foot is the correct answer here. So 35. So an HP 12 by 53 has if you think of the H, if you go from the flange to the flange, that's 12 inches. And then you cut 1 foot of that length of pile. You cut 1 foot, and then it would be 50, that would weigh 53 pounds. And so these other ones, the dimension of the pile from flange to flange in inches, incorrect. So that would be 12. And this one, the dimension of the pile from flange to flange in millimeters, no, because if this was a metric designation, this number would be 12 times what, 25 or something. So it'd be a bigger number. So again, HP 12 by 53, the 53 means pounds per foot. When ambient temperatures increase, the expansion joint opening does what? So we got to think about is what's happening to a bridge. The temperatures get hotter, what's going to happen? The bridge is going to get longer. So that's going to tend to make things at the end narrower or decrease. So most you got that right, that the joint would then decrease. False work must be, and here's a select all that apply. So there's a few here that are correct. Designed by the contractor. Actually, there might not be a few that are correct. It's this one. False work is always designed by the contractor, and they are responsible. And you, as the inspector or the engineer, are responsible to see that it is built in accordance with the plan. Constructed with the same material shown in the false work drawings. Yes, that is also true. And so the false work drawings are prepared by the contractor, and so the false work must be constructed with that. Now this one, meet the details shown in the bridge plans, that is not correct. I suppose that it's possible that there would be a bridge plan where false work is shown, but it's almost never. So this is incorrect, the middle one. Designed by an engineer registered in Minnesota. Yes, that is true. So this false work designer by the contractor, they hire someone who is registered in Minnesota. And then the last one, inspected in the field by the false work engineer and certified in writing that field construction meets the false work plans. That also is true. So actually the only one that's not true here is this middle one. And so all the other ones, designed by the contractor, same materials, engineers registered, and they inspect it and sign off on it. All of those are correct. Which of the following is true for bar number B915E? Okay, so we have different designations, and we will get into this a bit. The B is often, where is it on the bridge? The 9 is the number and the size of the bar. The 15 is kind of a numerical placeholder. So the correct answer is the 9 would be in 1/8 of an inch. So it's 9/8 of an inch. So we know that much. The other things we know is the E means it's epoxy coated. So the diameter is 15 millimeters. No, that's not true. This is just a designation. The 15 is a numerical. You have B901, then you might have B802, and this is a designation that increases. So correct answer is the bar diameter is 1 1/8 inches. That is true. And the bar is epoxy coated. That is true because of the E. So the 9 means it's 9/8 of an inch or 1 1/8 inch. And the bar, 915 inches long. No, we'd have to look at the bar bend details to find out what is correct there. How many points of support must be provided prior to bolting steel girders under both line assembly and full assembly? And so this one is 3 points of support, and including the shoring towers. So I'm not sure if it's Nick or who's going to be presenting that, but when we put together steel beams, oftentimes there needs to be a false work support, a shoring tower. So you might have abutment, then shoring tower, then pier, and so then you're good to go on. So it takes 3 points of support, and it does include the shoring towers. MnDOT spec book allows these options for controlling bolt tensioning in the field. Again, select all that apply. Turn of the nut is allowed. It's a method. It's been around for years, but it's still valid. And it's you tighten the bolt up to a snug tight, what we call snug tight fit, and then you go a certain number of turns or portions of a turn, depending on the size of the bolt. Snug tight is not correct. You get it to snug tight, and then you do turn of the nut. A direct tension indicator is one that's used often nowadays. So these two, direct tension indicator and turn of the nut, are allowed. This one, inspector closely observing tightening procedures on 50% more of the bolts. No, that's still not. The spec book allows turn of nut or direct tension. If they're using turn of the nut, I suppose you could say then the inspector should be on site to watch their procedures, but by the spec book, that is not allowed. Field welding can be performed by persons who, and select all that apply. It's really, they are certified by AWS for the weld procedure being done. And then they must have some documented work on similar welds, and I believe it's the past year. Mark, correct me if I'm wrong on that. But all these other ones, it's good, you know, more than 5 years welding experience, good, but have you done that welding procedure? Have you done an overhead fillet weld, or, you know, whatever the case may be? Have graduated from tech welding program, you know, certainly wonderful, but no, you still need to be certified by AWS and have been on 3 or more bridge projects in the past year. If you haven't done the welds, you know, then it still doesn't apply. The pre-stressing strands typically used in fabrication of pre-stressed girder has what ultimate tensile strength? So this is one, you think of the pre-stressed girders, and they're high tension. The 270 KSI is what it is. So I like to say when I was explaining things on the St. Croix project, one of those strands has enough ultimate strength that it can pick up a fully loaded 80,000 pound semi. So 270 KSI, that's 270,000 pounds per square inch. So it's really high strength material. These other ones, no. So it's 270. Which of the following is true for type 2 special surface finish? So type 2 is a single component mix. Type 1 is a mixed up, there's 3 components we mix up, but type 2 is a bucket mix, single component. It can be applied as soon as forms can be removed. So it's one of the benefits of the type 2. This is incorrect. It's not a 2 component, it's a single component. This is true, it must be on the APL. This one is false. Concrete must cure for 28 days prior to application. So it's a single component. So type 2 just it kind of goes against the definition, but type 2 is a single component mix, can be applied soon and on the APL. Which of the following curing methods is allowed for bridge structural slabs? So conventional wet curing, and this will again select all that apply. So conventional wet curing within 30 minutes after carpet drag. This is the main one that happens. So we're going to talk, when we talk about superstructures, there's structural slabs that are underneath a low slump wearing course or a chip seal wearing course. It's not so critical that you get a fine finish on there. What's critical is you get a good cure on there. And so the conventional wet curing within 30 minutes is what is needed. AMS sprayed as soon as possible, that'd be a no, because we're going to put on a concrete wearing course. And if you put AMS on there, you're going to have a bond break and you're not going to be able to adhere. Berlin, placed within 30 minutes. This is an old technology. Berlin is no longer used. So now it's conventional wet curing, which is wet burlap with a white plastic sheeting. And then this one, a conventional curing placed as soon as concrete can be walked on without marring the surface, also incorrect because we want it within 30 minutes. Sometimes you can't walk on there. In fact, I'd say most of the time you can't walk on there without putting big footprints in. This is what used to be back in the day a common spec. Which of the following are repairs of concrete bridges? So concrete. Type A, B, and C deck repairs, yes. So concrete decks, that's one. Tack welding, that's a steel. So welding would be on steel, so that's not a concrete repair. Shotcrete is. Shotcrete is a lot of times on pier caps and things like that, columns. You'd be doing shotcrete repairs. A crack sealing by a chase method, yes, that is. Bolted splice plates, no, that'd be steel. So that's not one. And then scarification is one where you're taking off a little bit of the top of the concrete deck. So that also would be a concrete bridge rehab. How often are continuous, transverse, and longitudinal bars tied on the top mat of a bridge deck? So at every intersection, at every other, left up to the iron workers, or staggered. So it is at every intersection. So when we talk about superstructure, we will be talking about that. The bottom mat can be every other intersection, but the top of the deck because that's where a lot of people are walking on. It's every intersection. So we can't just leave it up to the iron workers. We need to know, what do the specs say? And then be able to move forward that way. Okay, so good job, everybody. Let's take about a 5-minute break. Every on the hour, I like to keep it at least, so we don't get stuck. So my computer shows 8:51. It's probably close to 8:52. So at 8:57, we'll get going on the next presentation, unless anybody has questions. I don't see any. So 8:57, we'll reconvene. Okay, welcome back. Start to get into some of the historical aspects of bridges. I think to be a bridge engineer, a bridge construction engineer, field engineer in the bridge area, it's always good to understand what the structural concepts are that we are dealing with. And we certainly can learn a lot from history. And this first presentation talks about some of the historical things, a couple of the failures that have happened, and what we as engineers, technicians, project supervisors can learn about bridge construction. How can we make it better going forward? And that's really, I would say, the goal. All of us who've been in bridges, and I've been in bridges essentially my whole career, 37 years now, it seems like you're always learning. After every project, you say, boy, I wish I had done something a little bit different, put something different on a set of plans, recommended something a little different, did something different in the field. And so we learn. And that's part of what we're going to do here is go through this slide, which is these slides, section 2.01, bridge styles, historical perspective. So to generate really a general understanding and appreciation of the processes to go into bridge design, that's what we're trying to do here. We don't have a ton of time. We have 3 days. We're packed in here as it is. So we don't have an overabundance of time. We have time to get into a fair amount of detail, but we're not going to get like the 2-week bridge construction class gets into even more detail on a lot of these things. Each of you, so we had, when we did that little survey, the vast majority of the class has less than 3 years of bridge experience. So you come armed with a little bit of information and knowledge, but your experiences in life of how you look at things are going to be different. And so some of these sessions are going to be perceived a little bit differently. Hopefully you can gain from this some things that will help remind what's going on. So if nothing else, maybe we stimulate your curiosity. I've loved being in bridges. I think they're just fascinating to work with. And so hopefully we can impart some of that curiosity and subsequent knowledge onto you guys. So bridge, the word bridge itself, it describes a huge class of structures. And
Paul, this is
Yep.
Erica.
Yep.
We still see your Mentimeter screen.
Okay, you see it now? Are you seeing the main presentation?
Yeah, it's developmental perspective. It's blue.
Okay. Sorry about that, guys. So the first slides were just in general. So we'll just stay right here with this one. So the name bridges, it can be a multitude of things. Obviously with MnDOT, with the county, your bridges are going to mainly be carrying vehicles. But there are bridges that carry utilities. There's bridges that carry all kinds of things. Some of our bridges are only pedestrians. Some of them are roadways over pedestrian trail. So there's all different facts. So we're going to move kind of from the general to the specific, meaning we're going to talk in general about what a bridge is, and then some of the materials, and then concrete. How do you produce concrete? How do you cure concrete? Things like that. So we'll get down into some specifics as we move forward. It says here some things don't change. Well, some things do, but basically a bridge has a definition of being able to carry something, vehicles, people, utilities over some obstacle. So this Clapper Bridge is one of the old bridges that, it comes back that somebody figured this is a pretty good deal. Let's stack up some stones in the river, put some slabs across, we can walk right across it. Or the beam span, shown on the right. Those of us, if you think back to our childhood, who of us didn't make some kind of a little bridge over some little trickling stream of something? So that's the start of a beam span. That's the start of bridge construction. So what are some of the basic construction materials? You just look at it like a tree. There's a multitude of things that come off it. Some of those early people used stone. We're going to see some bridges of some of the limestone block that was used for stone. Wood, obviously, people chopped down a tree, put it over the river, and they had now a bridge. Stone could be made into building blocks. It can then be natural aggregates. Later on, they figured out how to make cement. Cement is a constituent of concrete, and so wood, you get glued laminated, you get hydraulic cements, admixtures. Then there came the advent of iron, and after iron, then there came steel, and so we'll see some pictures of some of the first steel bridges that were made, and now we have high strength and high performance steel. And went from riveting and bolting to now there's welding, and all those things are improving. Rolled steel beams. Then you get to concrete itself, made up of the cement, the aggregates, and the water. There's plain concrete, then there becomes reinforced concrete. Enables us to make bigger and bigger bridges with less and less material. And so that's where the precast and the pre-stress comes in, post-tension. We'll talk a little bit about some of that. What's in the future? Who knows? But what we do know is that there have been huge advances in material in the last 100 years, last 200 years, last 50 years. So those are things that we look at. So fundamentally, what are the structural elements? The basic structural elements include some of the blocks, the arches. Then you get into beams when you start, shaping say a big wooden timber or log. We can do those kind of things. Corbel arches. We're going to talk about that in an arch bridge of how that came to be. A Bourgeois arch, a different kind of an arch. There's vaults. There's different arches, simple spans, composite beams, continuous. Then, it's one thing to span from pier to pier with one beam. It's a whole nother thing to go across the three supports. And now you can actually make that beam work a little bit better when it's continuous. Axial elements like columns, tension elements like in trusses and so forth. So there's a lot of things that happen there. Trusses, there's different types of trusses like the Pratt trusses. Cables, we utilize a lot of cables in post-tensioning. I worked on the St. Croix Bridge, a 5-year project, and a lot of cables going on there, plates and suspension, cable stay, things like that. So again, what does the future hold? We don't know. But what we do know is it's going to keep improving. And you guys, as the bridge builders of today and tomorrow, will help make that happen. So just to look briefly at some of the structural components, and we'll handle this in both just briefly here and in the next section as well, that bridges carry loads or forces in different ways. And some of the main ways are tension and compression. So tension is trying to pull something apart, compression is trying to push it together. Bending is you have a flat or horizontal element, and then you impart a load and it bends like that, and it doesn't have to be horizontal, it can often be vertical. Torsion is you have an element and it's trying to kind of twist itself apart. And then shear is a type of a force that tries to split an element. And so we'll be talking about some of those. And so the bridge elements are designed to resist the forces in different ways. The job of a bridge engineer is to design it so it's efficient. So you don't overuse the reinforcement, you don't have too big of a size, and so forth. So those are all things that you'll want to keep in mind even as you're building it. So a little diagram of what all those things are. So in a bridge, many elements that are, I put here, most elements have some type of bending moment that results in both tension and compression at various points in the element. So like on the top picture here, we have a pier cap. And we see how the beam is coming down, for instance, right in between two piles. So that's actually imparting a small, maybe not even a small, it's imparting a bending moment in here. And it's going to result in some tension on the bottom, some compression in the top. And so the pier cap is reinforced to counteract that. This is a picture from the St. Croix project. That there's an awful lot of reinforcement that goes in there. And there's a lot of compressive forces that happen. There's these white elements down here are post-tensioning ducts. There's that 270 KSI material we had in the quiz that runs through here. So that helps it to, it puts all the material into compression. So when a load comes on top, the concrete will remain in compression. So shear is something that is addressed through the use of these what are called stirrups. So oftentimes shear would manifest itself by a crack that goes diagonally. And so these bars that are vertical are called shear stirrups or shear bars. And the same down in the bottom right picture, those bars also are called stirrups or shear reinforcement. So just looking at some of the past history, bridges started out a lot of times with arches. So the arch was the first major engineering innovation. Here's the Roman construction at Alcantara, Spain in 100 AD about. But among the things we see here is this arch shape. And the next slide will show about what the different configuration of arches have been over time. And so early on, it would have been a basic post and lintel. You stick a couple of logs up this way and a log over here, and it's called a post and lintel. You can then put a roof on there and some walls, and you have a nice, safe, dry place to dwell. This corbel arch. So a corbel is like a little piece of concrete or material that would stick out the side, in essence, cantilevering over. But a corbel arch then uses some of this material that's back here to counteract this little bit that's overhanging. And so you just consecutively overhang a little bit more until you form an arch. So that's called a corbel arch. And then a Voussoir arch is this one. It's more a true arch, and it's made up of pieces that fit together with a keystone block in the center. So that was one of the early age inventions to come. So there's a little pronunciation here of Voussoir arch. Okay, foundation construction. big bridges like that one we saw in Spain, built in the water, it takes a lot of effort. And cofferdams are shown here. Early cofferdams are a couple of rows of piling. You put some clay in the center, and then you go and you dig out down here. So in essence, what you're doing with any kind of a cofferdam, making it watertight so that you can take the soft soil out, so you can get down to the firm information, or firm strata, firm foundation materials. So the early builders became adept at building this, but they would wait for low water and they'd maybe do one foundation a year. So you can see that bridge takes a while to build. We start looking at what happened then in this country. This guy, Squire Whipple, and it's his name, it's not a title. He was born in the early 1800s, and he patented this combination of an arch truss in 1847. But he looked at it as a way to study what's going on. What are the forces? What are the strengths and so forth? And so he published then a book, and this is a picture of the book and then some of the information that comes in it. And in here we see that he didn't say, well, let's just build a bridge, but let's build a bridge and let's understand what's going on. And so he looked at this as a way to figure out what the forces were, how big of an element you needed to make it. And if you have different configuration, do the forces flow differently? So that's really some of the things that went on. But some of the greatest bridges in America were constructed in these years, between 1870 and 1930. And there were record lengths, and the next slide will show that they haven't even been surpassed by that many bridges since. So you're looking at that 50-year time frame. Suspension bridge over the Ohio River, 1,000 feet. By the time you got to the Brooklyn Bridge, you're 1,600 feet. By the time you get to the George Washington Bridge, 3,500. And just out, I don't know why this one wouldn't be in here, but the Golden Gate Bridge, then 4,200 feet of a main span. All of these being suspension bridges. But some of even the longer ones you get now, yeah, you've gone another couple thousand feet, but just look at back using the technologies they had 100 years ago, nearly 100 years ago, and they're able to build bridges with 4,000 foot main span. So some of the early Minnesota bridges, I just added this one on the right because it's kind of a cool one that when I was on the St. Croix project, I went and looked at this one a time or two just to see what the old time bridge builders did. This was actually built in 1865, Stillwater Township. It's Browns Creek. And so this is, again, one of those Rousseau arches, as well as this one, a masonry arch. So these, bridge builders found the masonry from the limestone bluffs, and they'd cut them out. This one in 1865 was part of the, it's called a military road, Point Douglas to Superior. And that helped bring provisions up to the northern part of the state and so forth. So important in even the history of the state. Some other bridges, the 7th Street arches in St. Paul. So again, we see arch construction was kind of big back then, and they did a lot of bridges with them. Some of the early trusses, here's from 1883, the Kennedy Bridge, and a Pratt through truss. It utilizes these tension diagonals. So we talked about tension and compression, and a bridge engineer would figure out what's the tension that's going in this member, how big does it have to be to resist those loads. But essentially, if a vehicle goes on this deck right here, there will be some stringers that will translate load to the floor beam out here to this lower cord would come here, but eventually the load has to get itself back to the point of support. And so it'll go through a tension member, and eventually loads will work their way back here. So interesting bridges. There's still a lot of these that are around. Here's another one, another Pratt through truss from 1904 in Rice County. Well, it's good to see some of these. Cedar Avenue bridge, renovated recently. This was a reinforced concrete arch, so we see a lot of these ones with the either open or closed spandrel columns in here, the arch ribs. So, got 265 feet on that bridge. A Robert Street Bridge. This is really an interesting one. There's actually structural steel inside of these arches, and then it's encased in concrete. So, those are things that are done as well. So what about historical construction management? You folks are going to be in construction management, at least a lot of you will. What has happened over the years? Here's one, the Firth of Forth Bridge, famous bridge over in Scotland, built in 1890. It took 7 years, 1882 to 1889 to build. And just looking at some of the information, at least 57 men died during the construction, and possibly as many as 73. So, I mean, that's like 10 guys a year almost, 7 to 10 guys a year. Piers were made of granite. They took 3 years, but it's a cantilever construction. And it's also the first major structure built of steel, not of iron. But you just see of all of the lattice lacing and so forth that goes on there. And a lot of times it is construction techniques. There have been a lot of disasters over time. This was a Quebec bridge in 1907. There was actually just a presentation at the University of Minnesota a couple of weeks ago talking about the history of some of these tragedies in bridge construction and kind of how every 30, 35 years something tends to happen. And it's as we get maybe more complacent in what we're doing and you forget about the need to look at some of the details, things can start to happen. So just some pictures there of what happened. But the need for construction management of bridges is not a recent development. So this means that as they were going out there, you have to support the cantilevers and support everything so that it can go together well. Brooklyn Bridge, there's just a ton of information on the Brooklyn Bridge. John Roebling, gap on the top right, is the one that was the driving force. He designed it. His son took over, but his son actually ended up getting injured on the project and down working underneath the water. But 1883, and it took 13 years for construction. The main span is 1,600 feet. But this is what they did back then. So the caissons, they lowered stuff down, but the workers would come down the shaft, and then there was like an airlock system that would happen, but they'd be working down there, and they actually got some of them the bends. So this bullet right here, decompression sickness suffered from exposure to conditions of high pressure. So even though they were under the water, they were working in the dry, but there's high pressure down there, and they suffered what's called the bends. And so when Washington Roebling went down, his wife, Emily, assumed the management of construction. And so she kind of coordinated between them. So just a lot of interesting lessons in history when you think of it. But the guys that were working down here, they're called sand hogs. There's some really interesting information of how they would make that with compressed air, a blowout pipe, but there'd be an airlock to get down there so that they can work without the water coming in and drowning them. Quality control became apparent on the Brooklyn. The supplier of the wire, it was caught in a scheme to supply substandard wire, and so the cables on one side are larger than the cables on the other. Okay, so what's going on? What's changing? The world is changing. Bridge construction has always been a complex undertaking. I worked on the St. Croix Bridge. It's complex. It's extremely complex. There's a lot of details. that go into it, but it's always been that way. And so to be then in construction engineering, you need to understand what are the forces, what are the loads, what's going on. Contractor wants to do something one way. Can you say yes right away, or do you need to say, hold on a second, we got to think about what's going on? So, you know, that's just a reminder about that. So today's bridge construction, it's continuing to be more complex. So this is a bridge, I think it's from the Parkway, Blue Ridge Parkway in Tennessee. Beautiful, beautiful area, beautiful bridges that were built, but you can see the box girders, everything fits together, and end of the day, it has to fit where it needs to go. So important to do that. Lowry Avenue Bridge, very complex pier shapes. 3D, you almost have to have 3D. And we're going more and more to 3D. At WSB, we're doing some design of bridges in 3D. And it's pretty interesting to be able to look at that and look at where are some potential conflicts. Hastings Bridge, this one was incredibly fun to watch go up, but it's a tied arch. It was built on land, so to the left of this top left picture, about a half mile up the river on the Mississippi, there was a staging area, and they built this whole bridge there, and they moved it in. Actually, we should probably put a picture of them. They had a system of cables to pull that thing up into place, and it was really incredible to watch. Cayuga Street Bridge, there's a lot of complex geometry here, bridges that got ramps coming in and out and things like that. So a lot of complexities. Lafayette, this is a big steel box girder. These plans were prepared with both steel and concrete. And so that was handled there. St. Croix Bridge, I was on this project, and again, an awesome project to be involved with, but very, very complex. So with that ends this session of 2.01. Anybody have questions? And again, I can't see the chat box. Mark, if anybody has any chat questions, or even I can't.
No, nothing has come through, Paul. I've been watching it.
Okay, chapter 2.02 is talking about structural elements. There'll be a few things that are a little bit similar to what we just talked about. So again, if you have any questions, Mark will be monitoring the chat box. You can type them in. That's probably the easiest way. Again, I wish I could see them, but I can't see chat questions. So, but we will go forward here. And all right, what are the goals for this chapter? We want to understand what are some of the words and terminology. We mainly deal in steel and concrete. Steel can be steel beams and girders. It can be high strength steel. It can be reinforcement bar. It can be different grades of reinforcement bar. It can be 60 KSI. It can be epoxy coated. It can be stainless steel, which is typically a little bit higher. It can be pre-stressing strands. Concrete can be many, many different grades. And as Maria comes in to talk about concrete, you'll see that there are many different grades of material. Concrete can be cast in place, and it can be precast. And precast is often in a fabrication plant. Sometimes it might be on site in some facility, but mainly in some type of a plant. And so all of these materials, steel and concrete, gets combined into structural components, which sometimes we call elements. And elements are going to be beams, are going to be pier caps, columns, decks, things like that. And then those even form an array of structural systems. And the structural systems might be the superstructure, the substructure, things like that. So we showed a concept about some of these items: the compression, the tension, the bending, and then the shear. Torsion is not on here. That's another stress, but this depiction says there's 4 ways material resists the forces, and torsion really does it. It manifests itself into these 4 as well. But of compression, like I mentioned in one of the earlier presentations, is compression is really trying to push things together. And so things like columns are typically a compression member. Tension, you're trying to pull stuff apart. So any kind of a cable will be a tension member. The shear can be 2 different ways. A sliding shear on the bottom of this center top picture is like a bolt holding 2 plates. And if you slide them together, that's the sliding shear. But now there's also vertical shear. If you have a beam going across, there's a shear force that's trying to split that. A horizontal beam is trying to split it vertically. And then bending, we spoke about that it's imparting its own forces. In a case like this, there would be tension at the bottom, there'd be compression at the top. So direct stresses mean, that's exactly what it is. It's just, it's going in one direction. Bending, though, it manifests itself in different ways. So what are the bridge families or types of highway bridges? So basically you could say there's slab spans, which you have a thicker concrete slab or deck that the traffic is driving on, and you use a thicker section to be able to span a little bit further than if you just had a 7 or a 9-inch thick deck. And so slab spans, beam spans, then they put a beam underneath the deck so the beams can then span longer. Rigid frames are kind of the abutment and the deck all framed together. So it makes kind of a inverted U, so to speak. Box girders, there we get into some post-tensioning. In the concrete world, we get into high-strength steel in the steel world. And then there's other types, culverts. We're not going to really talk too much about culverts in this class, but it's a huge, huge number of bridges in Minnesota are culverts. Trusses, cable supported, things like that. So, many of these, like say the St. Croix, is called an extrados bridge, and it's a combination of a segmental post-tension and a cable supported bridge. So again, many different types. But when we look at bridges and we look at bridge engineering, a force is what we're trying to resist. And a force is the action of one body on another that affects the state of motion or rest on that body. And so when we're looking at bridges, what are our main loads? Our main loads are going to be dead loads, which is the weight of material itself, the weight of concrete, the weight of steel rail, your rebar, your structural steel beam, many, many things like that. It can also then be a live load. So a vehicle driving across the bridge, as it gets onto the bridge, it's imparting a force or a load or a force onto that. And then the bridge has to distribute those forces. And so for all these things, then we have to look at what is the point of application? And what's the magnitude, meaning how big is it and what direction is it going? And so, some of our loads, like there'll be wind loads that are considered. Or maybe on a bridge in a river, there's ice loads. That ice breaks up and it comes down and it hits on a pier. We need to know what is that load, what's the application, the magnitude, and so forth. So a simple structural system is if you build a little shelf in your bedroom, what are the forces going on there? And I'm sure everybody would know, if you're going to build this little frame, what's more important? Do you have to fasten this thing into the wall, or do you have to fasten this thing into the wall? Well, I think we can all kind of understand that it's probably more important that we get a good sound connection to our upper one. And so what we would see from that is, if we put a 200-pound force on this, it's going to manifest itself into some tension and some compression that are going on in that element. So this little thing is a convenient way to look at structures. But the point and magnitude of that force, so now we have 200 pounds that are coming down here. It has to translate itself through this member to get into the wall so the shelf doesn't fall down. And so you have a 200-pound vertical force that's going downward. You then have a tension element, and as you mentioned, if you're going to fasten this thing to the wall, this is going to be important. Well, why? Because it's a tension element. It's trying to pull apart. And so a little depiction that would show, what it is. So what's the magnitude of that thing? You use all of the things that we've learned in geometry and algebra and math to depict what are our numbers. So in this case, you'd use our formulas to show the magnitude is 346 pounds, or like it's mentioned here, negative 346. So it's a 346-pound tension. So a 200-pound load here makes a 346-pound tensile load here. What about the compression? So we do the same thing. That's 400 pounds. So now you have a 400-pound compression going on there. So we see the 200-pound load, when it has to be put into elements that are horizontal or diagonal, those forces actually increase in that situation. So another term that we use in bridges is stress. And what is stress? Is a term to describe the intensity of a force, and really it's a force that's acting on an area. So we've already mentioned many times, like, what is the common rebar? It's 60 KSI. That means that rebar is able to withstand 60,000 pounds per square inch of material. So if you have a rebar that's 1 square inch, it can withstand 60,000 pounds pulling in a tensile direction. So, but stress is the internal resistance to an external force. And then direct stresses are those stresses that are uniform over the entire area. Okay, so the concept then of stress, using this little small lowercase f is a symbol for stress, is the P over A, which is the axial force. So the P is designated as a force. Over the A is what is your area of the material that you have. And so here is just what those symbols mean. So just basic engineering formulas are shown right there. So why do you as a field engineer need to know that? Because you need to know when somebody wants to use a different grade of rebar or a different grade of concrete or something, it makes a difference because the engineers have calculated it to be for a certain amount. So here's just a depiction. If we have a 6,400-pound block on top of an 8x8 post, what kind of a stress is on there? So you just literally, you take the area is 8x8. So you have over here 8x8, so it's 64 square inches. And so you take the load of 6,400 divided by 64 square inches, you'd have 100 PSI. And so in material engineering, then we'd say, is our block able to withstand 100 PSI? It's not a very high stress, so we'd probably say, yep, that might be good to go. So compression elements. Here's a picture of the St. Croix Bridge. Massive bridge, but skinny little piers. You can't really see from this view, but there were 2 different columns in each one. The skinny dimension, so going in and out of the picture right here, was 4 feet. So 4 feet by about 20 feet wide. But you can imagine a small little oval like that. But the load of 600 feet of bridge span, and actually half of that from one way and half from the other, are coming down these columns. But this, they're mainly compression. So columns are mainly compression. And as a result, there's a lot of shear reinforcement. You need to watch the buckling. There's a lot of things that we design there. Tensile force. So here it's It's a 1,500-pound load with a 1/2-inch diameter rod. So again, stress being the internal resistance to an external force. The area of a 1/2-inch rod, so you do your pi r squared or your pi d squared over 4 to get the area of the rod, and then you can calculate your tensile stress. So in that case, 1,500 pounds, so 1,500-pound weight divided by that area, you calculated 7,655 psi, or that's the same as saying 7.65 ksi. So here we see the terminology that we often use in bridges is ksi, just to make the numbers a little more manageable. But it's the same as 7,600 psi is the same as 7.6 ksi. So just a little picture up here of the St. Croix project. The only stress that's in those stay cables right here is a tensile force. It's trying to keep these segments from falling down. So only tension is in there. The bottom picture is a steel beam. Oftentimes steel beams are used for their ability to carry tension. And so they also enable us to connect more complex type of structures, like this is a single point intersection. Shear stress. So this is one where, again, if we have a beam and then there's what's called a shear stress at the ends, it's the highest. And it's the kind of the parallel area. So it'd be whatever the area of that beam is. And so in this case, the unit stress is shown as this, the smaller case F with a small v, but again, it's the P over A. You see that similar formula coming at all of these things, but in this case, it's the area of the shearing force that it's trying to pull apart. So in a case of, here's a case of a rivet or a bolt. So these plates, if say this is in tension, they're trying to pull apart. The purpose of a bolt is to clamp those together so they don't pull apart. And then you can do calculations to show, what's the force that's in there. So in this case, 5,000 pounds. You can calculate the area of that 3/4 inch rivet is 0.44 square inches. Do the math and you get 11,000 psi is the stress that's going to be in that rivet or bolt. So we had shown this picture before, but again, shear stirrups are used to withstand those shear stresses. Vocabulary is a lot. Here it says education is 80% vocabulary. So what do we know about our bridge terminology? Let's talk about strength. Strength of material, its ability to resist forces. And so again, we see these things coming back time after time after time: compression, tension, shear. Those are things that need to be resisted. And we're designing and building bridge elements to be able to resist those forces. So the ultimate strength of material is the unit stress that causes failure. I think a lot of you have probably gone through engineering school. You've gone through some of those formulas and shown, like, for instance, a steel, the curve would go up and then it kind of tapers off and then all of a sudden it falls off. Well, that's the ultimate strength. It can't take any more load until boom, it fails. And so that's the ultimate strength of the material. The same with concrete. Concrete's not very good in tension, but it's good in compression. What's the ultimate strength of that stuff before it would break? Sometimes we use terms like elastic and plastic. There's a couple of slides here. Elastic is applied to the greatest unit stress a material can resist without a permanent change in shape. So that means if we have a steel beam, for instance, and we drive on that and we deflect it down, if it's still within that elastic range, the vehicle goes over, it bounces back up. Or we have a tension member on a truss, we pull it and it deforms a little bit, but it doesn't elongate and not go back. So we want to stay within that elastic range. Stiffness. it enables a member and an element to resist deformation. And so you can imagine if there's a block of wood and a block of steel of the same size, and they have the same compressive load, wood block would become shorter and it would compress. And that's just because of the stiffness of the member. So the stiffness of wood is maybe 30 times less than the steel. So elasticity then is a property that enables it to return to its original size and shape. With many materials, there is then a unit stress beyond which it doesn't regain its original dimensions. In fact, we'd probably say everything does. Sometimes there's brittle failures, which we talk about, and so forth. But again, that elastic limit, we want to stay within that elastic limit. Sometimes that's called a yield point. Plasticity is the opposite. It's a perfectly plastic material that doesn't return to its original dimension. So, you know, the kids at home are playing with Play-Doh or something, and they squish it and it stays in that shape. So that's a perfectly plastic. Ductility is something that in bridges we want to know, especially in steel. What is the ductility of that member? So it's a property of a material that permits it to undergo plastic deformation when subjected to a tensile force. And, you know, in Minnesota, we've experienced 2 weeks of extreme cold. You know, for instance, our dog has gotten off his chain twice because he snapped the little hook that we have on the little pulley. Well, it gets so cold that that material gets brittle. It's no longer ductile. And so this slide talks about the brittleness, and on bridges, it's an important concept. We want to know what our material is, and so the properties of steel, we need to know what that is. So when a body is subjected to a force, there's always a change. Those are called deformations. So again, a block subjected to a compressive force shortens in length. If a tensile stress comes, it's going to make that thing be a little bit longer. And if you have a beam, here's where the deflection, the bending comes in, but there will be a deflection that will happen. And as we talk about superstructure elements, we will be talking about, you know, we need to be able to predict that deflection. So whenever there is stress, then there is there's always an accompanying deformation. And sometimes it's so small we don't even see it, but that is called strain. And we often use the phrase stress and strain. We're not going to overly worry about that, but you know, they kind of go hand in hand. Modulus of elasticity. In the field, you're not going to need to know this too much, but the bridge engineers need to know this for the properties, what's the deflection is going to be, and so forth. It's represented by a letter E. Essentially, it talks about the unit stress over unit deformation. There's a lot of formulas that are applied. Real common formula here, E is PL over AE, where P is the applied force, L is the length of that member, A is the area of the member, and then E is the total deformation in inches. And then you can likewise put across the deformation in inches would then be this PL over AE. So oftentimes our engineers are using this version of the formula to look at deformation. So looking back again at those, so bending does respond differently than the other elements. So let's understand it. What are some of the terms that we use? So we need to understand the loads, the supports, what are the section properties. We can calculate then a bending moment, and what are some vertical shears and material which goes on. So loads can be classified with respect to time, and they can be classified relative to the area over which it's applied. So A semi going across a bridge, it comes, it parts its load, and it leaves. Others, like the dead load, you always have the weight of the concrete deck that's acting on those beams. Little depiction here of what happens. So static loads, temporary loads, and impact loads. So these static loads are called dead loads. And in this little depiction, the weight of all of this material, this building, whatever it is, so say it's even a bridge, that's always there. And it's coming down through these columns or a wall, or whatever. There's always going to be that load. This person on the ladder, now that is something that's a temporary load. So those are called live loads. And in our bridges, that might be a vehicle going across. It might be a braking load. It might be ice on the river. And so different things like that. And then there's impact loads. And so here's just it's going to crush that building. But on bridges, that can be things like you have an approach panel that's settled and a semi comes up and it launches itself onto the deck and you have an impact load. So we're always looking at that. We look at concentrated loads versus uniformly distributed loads. So concentrated load is like a wheel load. And when we're designing a deck, for instance, we're going to look at what is the impact of that one single wheel load in that small little area, and how can those loads get to the beams? They can also be non-uniformly distributed. A couple of depictions here. So this is more a point load. If you had, this is a depiction of, say, a wall, a girder, and you have a couple of columns coming down. That's going to impart a force that we can call as force P1 and P2. And this orange beam, we can figure out what are the bending moment properties of that. Well, if it's a little bit different, and now we have a whole bunch of little joists coming in instead of two columns, we can start calling that a uniform load. And so that means, over whatever length, you'd have a similar, or you'd have a unit load going on that. For things like retaining walls, it's going to be a variable load. And, we've probably all seen this, where if this is water, it can also be the same for soil. You have no load. If you put your hand down right here, there's no load. But if you go down here, say you're in a swimming pool and you go down, there's a lot more pressure that's going on. Well, the same thing is happening in structures. And so down at the bottom of that wall, there's a lot more load, a lot higher magnitude of load that goes on there. So, we're considering that. And when we look at things like abutments or retaining walls, we will see that there's more reinforcement down in the bottom of this wall, and especially in the back bottom of the wall, because it's trying to resist this higher bending moment that's going to be a result of these higher loads down at the bottom. So when you get up to the top of the wall, you don't have much need for the reinforcement at all. Okay, there's many different ways of supporting our bridges. So beams can be simply supported. I already mentioned continuous, 3 or more supports. They can be cantilevered, overhang. They can be restrained or fixed. So there's some depictions here. So simply supported is just, as it mentions, there's 2 supports. You have 1 beam. You have loads that are on that beam. And it's going to be a simple moment diagram and simple shear diagrams that would be a result. But you can continuous, you go across 3 or more supports, it actually becomes more efficient. We have now negative moment over the piers, positive moment in the center of the span. But what they tend to do is they will even themselves out. So it won't be as big of a positive moment, and you'd have small negative moment over the piers. So it can be more efficient for the same number of spans than if we had simple supported beams. Sometimes there's cantilevers. with a load out on the end. And so there'd be some heavy conditions here that we need to be analyzing for. It can be a support going over with a load out here. This is something, like a needle beam used to support an overhang for deck construction. So this is the kind of a load configuration that we would have. So there's a lot of different things that we can get to, different depictions of what happens. But here is some diagrams of what those things can be like. What does that mean then to us in the field as construction engineers building bridges? It comes down to what are the members, what are the cross-sectional properties of the members that you are building. That means what's the area of our concrete, what's the area of our steel, what's the center of gravity, and also what's the placement of our reinforcement. There are things we'll talk about briefly of section modulus and moment of inertia that we need to know for things like deflection, for the stresses, all those kind of things. So we'll talk about that briefly. The properties of the sections, they come out in different ways. Here's just some basic formulas. If you have a rectangular beam, the area is B times D. We're all pretty familiar with that. We can have the moment of inertia, the section modulus, and the radius of gyration. There's different formulas. Same thing with a circle, a triangle. There's different formulas that we can use. So the area shown there, center of gravity is kind of a center point of where things are. It's important so that we know where our reinforcement should be and things like that. It's the weight through which a resultant weight would pass. But an area has no weight, and so we look at that centroid as a way to calculate our thing. But what we really want, it comes down to things like this neutral axis. And what's the centroid of our member, and how is it going to rotate and bend? And so there's more sectional properties that show here. So neutral axis is the centroid point. So some of these are straightforward on a triangle. It would be different dimensions of 1/3 from the base or 2/3 from the height. So in a simple beam is subject to this. The fibers above a certain plane are in compression, and those below are in tension. And this is where that neutral surface comes into play. And so above would be in tension, or below, or vice versa. Above in compression, and below would be in tension. And so here's kind of neutral surface. This would be a rectangular block, tension down here, compression up here. And our designers are designing for this case right here. We're designing for the extreme fiber stress. We also look at sometimes, like on the St. Croix Bridge, on our deck section, we wanted to have zero tension so that if we don't want cracks to open up. And so in the compressive zone, no matter what the load case is, we want to always maintain that would be in compression. Moment of inertia, it's really how that material can resist the forces, but there's different ways that we can find moment of inertia. But one is like here's for a steel beam, and there's moments of inertia that are shown here. But the thing we want to point out, so this is a steel beam that's like an H shape. And if you are, there's a strong direction and a weak direction. And so if you're ever looking in a manual for information on moment of inertia or section modulus, make sure you know, are you talking about the x-axis or the y-axis? Are you talking about the strong direction, which is, your bridge is, your beam is vertical, or is that on side? And so just be aware of what that is. So the moment of inertia there, section modulus is similar, but now this is divided by the distance from the neutral axis. Again, you can look at the manual of steel construction or formulas to find that. And again, here it is. But again, I do want to point out the difference. So like here in the x-axis, the section modulus is 209 cubic inches. And the y-axis is 74.5 cubic inches. So you do need to be aware of what direction are we placing that member. So there's formulas. In college, this was a very common formula we use, BB squared over 6 for the section modulus in the S direction. Mentioned this before, that many elements have bending moments. They result in different stresses. We have reinforcement. We have post-tensioning ducts that are shown here to resist all of those stresses. So we really need to just understand what's going on. What are the structural elements? They're beams, arches, plates. The systems are the girders, the trusses, and you could even say super and substructure. So look again at this little chart, the slabs, the beams, the rigid frames. And so based on structural system, what are those components? And what kind of bridges do we have? So I didn't update this. I didn't have time to do that, but from 3-4 years ago, this shows that 57% of the bridges were pre-stressed concrete, 20% were steel girders, 21% concrete slab spans, and then a few of the other types. But we can see that nowadays we have a large number, the majority are pre-stressed concrete beams. So terminology, a cap or a pure cap, I'll just point out a few things. The span is from substructure to substructure. Columns are bringing the load down from the pure caps down to the footings. We got piling. In this case, this is a pile bent type pier. In this case, there's a footing with piles underneath it. So there's approach slabs, there's beams or girders. So a lot of different concepts that we have there. So typical, we'd have a beam span like this. The superstructure is the bearings and above, the substructure is below that. So that'd be the pure caps, the columns and the footings and the abutments. So a couple terminologies that we do use. For a slab span, it's a thicker deck. And so the deck is acting like a beam. And so it's going through them from abutment to pier. It takes a little more effort with false work to construct and so forth. So a simple beam, here's just a depiction of what happens. There's a deflection that we do, a pretty simple formula that happens in that way. A shear diagram is like this. So shear is 0 at the center and it's highest at the points of support. And the bending moment, the maximum then is here. And this was the deflection up on the top. So this in depiction, the compression on the top, the tension in the bottom. So when we build these different bridges, how big can we get? Estimated span. So pre-stressed girders they get up to 180 feet or so. Trusses can get 500. Boxes and you can get up there. Suspension bridges, we saw some of the suspension bridges were getting up to 6,000 feet. But kind of shows what that can be. So with that, we are now at a point that we're going to take a break. We've been going for a couple hours. Any questions? Mark, you got any in the chat box?
Nothing came through in the chat.
Okay, well, very good. Let's take a 10-minute break. So we'll take a break now until 10:15. And next up will be Ben Jilk talking about basic designs and key assumptions. So 10-minute break. Okay, so we're at 10:15 on my computer. So we're going to get back at it. One question did come in here at the break. So I'll briefly touch on this one. Somebody was wondering about what's the maybe what's the advantages of pile bents versus traditional footing foundations? Because the piles are uncovered. So one of the benefits of a pile bent, which is a pure cap and then piles going directly from the cap down into the ground, is that you don't have to build a separate footing. So especially, you think if you're in, say, in a river, you don't have to build a cofferdam and then dewater and then build a footing down there. But you can drive the pile right through the water, right through the soils, and to firm foundation. So very good question. And I think as we talk about substructures, we'll be talking about that. So next with us, it's going to be chapter 3.01, is Ben Jilk. He works with the MnDOT Bridge Office, and he's a complex analysis and modeling engineer. So Ben, welcome, and you can carry it away.
All right. Well, I turn off my video just so I save on bandwidth as I go here. So first, let's just look at the overall design process. This flow chart shows the basic steps involved in designing a bridge. We start out in preliminary design, where hydraulic studies, foundation investigations, and traffic studies, along with looking at site constraints, are used to determine the size and type of bridge. A lot of coordination is done with roadway folks in this phase to get the alignment and profile of the bridge figured out. Ultimately, a preliminary plan is put together showing all this information. Once a preliminary design is complete, the plan goes to final design. In this phase, the final designers take the information from the preliminary plan and determine the final geometry of the bridge and run calculations to determine the final details on the bridge. Oftentimes, the beam layout shown in the preliminary plans will be the same as that used in final design. There are times, however, that calculations done in final design will show that this doesn't work, and adjustments are made. With the final details determined through design, the final bridge plans will be drafted and special provisions for the project are written. The plan and special provisions then go off to letting, where the project will be awarded to a contractor. Note that this is the process for a design bid build project. Design build projects can have a different workflow. The structural design process involves several concerns, including load, geometry, staging needs, support conditions, site constraints, material, and performance. Other conditions such as economics and aesthetics enter into an iterative design process. Note that these conditions are initially of secondary importance to safety and serviceability concerns. Different bridge types can be expected depending on the span length needed. Short span bridges often use slab spans or pre-stressed rectangular beams. Mid-span bridges up to about 200 feet will usually use pre-stressed concrete eye girders or welded steel eye girders. Long span bridges up to about 500 feet have typically been steel eye girders or concrete box girders. For spans over 500 feet, specialty bridge types such as extradose or cable stay would be needed. Factors besides span length, such as site constraints, curvature, and aesthetics, can also come into play when determining structure type. When we design bridges, we have to follow a design code. The first standard specifications for highway bridges was introduced by AASHTO in 1931. These specifications have been updated many times since the original copy and have adopted different design philosophies over time. Original specifications used allowable stress design. Later designs used load factor design. In 2007, load and resistance factor design became the law of the land by decree of the FHWA and AASHTO. The current version of the AASHTO LRFD code is the 9th edition from 2020. MnDOT has its own bridge design manual, which governs the design of public highway bridges in the state of Minnesota. This manual generally follows the recommendations of AASHTO, but gives additional requirements and sometimes different criteria from those specified by AASHTO. These differences from AASHTO are based on MnDOT's past experience as well as comfort level with design criteria. It also gives best practices and general rules and assumptions to make in design. Finally, the manual also gives many design examples on how the code is applied. There are many different loads that need to be considered when designing a bridge. Loads that must be considered include dead loads, live loads, wind loads, thermal loads, water loads, time-dependent effects, earth pressure, extreme event loads such as vehicle collision, and construction loads. Ultimately, all loads that the bridge might experience during its life must be resisted by the bridge and be considered during design. Dead loads are a major load on the bridge. They have a constant magnitude and remain in one position or area. Basically, the dead loads on a bridge consist of the self-weight of the bridge, which include the girders, deck, barriers, and those sorts of things. Dead loads can act on either the non-composite section or the composite section. In other words, on the section before the deck is cast and on the section after the deck is cast, which contain different properties. Live loads are another major load on the bridge. Live loads are the loads that move across the bridge. They include design trucks, lane loads, permit vehicles, and pedestrians. The standard HL93 design truck is shown here. It is a major vehicle that we use when we're designing a bridge. It consists of a 72 kip truck. It is applied in conjunction with a lane load that is distributed along the length of the bridge. The design truck doesn't necessarily represent an actual physical truck. It is used to envelope force effects from vehicles that could exist in today's system. Once a designer has figured out all the loads acting on a bridge, they need to figure out which loads will act at the same time. In other words, what's the probability that all the different loads will be applied at the same time? This question has been addressed in bridge design with factored load design. It's generally not prudent to design every structure to the absolute worst case scenarios. In other words, it's not reasonable to assume that the full magnitude of all loads will simultaneously act on the structure at the same time. The next logical step is to recognize that there will be different scenarios of exposure to the various loads. These different scenarios are called limit states. Each limit state represents a different combination of loads to be considered. Another factor that an engineer must consider is the safety factor. All of us have some concept of what a safety factor is and why it's important. The question is, how safe is safe, or how do we measure safety? The answer to both questions is, it depends. Early in the history of engineering, the most common method of determining what is safe was the use of an allowable stress design. The allowable stress design is also called working stress design. It's a method in which the maximum stress a particular member may carry is limited to an allowable working stress. The allowable or working stress is determined by applying an appropriate factor of safety to the limited stress of the material. For example, the allowable tensile resistance for a tension member was 0.55 times the steel yield stress. This results in a safety factor of 1 over 0.55, or 1.8. Here we see an example of allowable stress design. In this example, the combined stress is taken as force over area. If moments are taking place, an additional component is added. For the example, with a force of 64,000 pounds on a post with an area of 64 square inches, the stress becomes 1,000 psi. If the material has an allowable stress of 1,150 psi, the check for ASD shows it to be okay. There are limitations of the allowable stress design procedure. Let's say that occasionally additional loads might be placed on the bridge. These additional weights might just be for seconds, and some might not weigh very much. Let's also say that some of the posts used might have holes of various diameters drilled through them. The traditional allowable stress method of design did not have procedures for the designer to easily consider these probabilities. Load factor design was the next philosophy of design that came after allowable stress design. For load factor design, the effect of factored loads is limited to the ultimate strength of the material. The factored loads are determined from the applied loadings, which are increased by selected multipliers that provide a factor of safety. As an example, one set of load factors would look like the equation shown here in load factor design. The latest design philosophy, which is used today, is load and resistance factor design, or LRFD. LRFD is based on the actual strength rather than an arbitrary calculated stress. It is an ultimate strength concept where both working loads and resistance are multiplied by factors, and the design is performed by assuming the strength exceeds the load. The underlying goal in design is for the capacity of the structure to be greater than or equal to the expected demand. The demand is affected by the type, magnitude, and placement of loads on the system and the interaction with the system's formal geometry. The capacity of the system is provided through a combination of material type, section, and formal geometry, and the system behavior under demand. The factored force effect in LRFD is calculated using the equation shown here. It is a sum of the products of these variables. The first variable is a load modifier relating to ductility, redundancy, and operational importance. This is typically greater than or equal to 1. The second variable is a load factor. The third variable is a calculated load. The total factored force in the post here is 64 kips. This table shows the load factors used in AASHTO for various load combinations or limit states. The load factor in the first column for the strength cases varies depending on what you are using and what behavior you are investigating. There are different load combinations for construction than for after the bridge has been open to traffic. This table shows the various load factors that would apply to the first column on the previous table shown. As you can see, both a maximum and minimum load factor are given. In some cases, such as when you are looking at maximum compression in a pile, you will want to look at the maximum load factor for dead load. If you are looking at uplift in a pile, for example, you would use the minimum load factor on dead load to maximize the uplift calculated. The factored resistance in LRFD is taken as a resistance factor multiplied by the nominal resistance of the member. The resistance factor is typically taken less than 1. In the example post, the post has a capacity of P sub R to transmit a load of that magnitude from the top of the foundation. Looking at these two equations together, the basic philosophy of LRFD is then to have the factored force effect be less than or equal to the factored resistance of the member. LRFD is based on probabilities. If you look at a bell curve of the load effect, the factored load effect used in design is taken on the far right side of the bell curve. This means that only a very small percentage of cases are anticipated to exceed the load combination used in design. It is impractical to try to capture 100% of possible cases, as the cost would get increasingly higher for very little gain. Similar to the factored load effect, the factored resistance used in design is based off a bell curve. In this case, the factored resistance is taken at the far left side of the chart. This means that a very small percentage of the time the resistance may be less than the calculated resistance used in design. When we overlay the two bell curves, we can see that the anticipated resistance will be greater than the anticipated load effect. Another way of looking at this is with what is called a reliability index. The reliability index is a way of looking at failure probability and considers the load effect and resistance. In AASHTO, the strength 1 load combination is set to have a target reliability index of 3.5. This equates to a probability of exceedance in the 75-year design life of 0.02%. There are many benefits to using LRFD versus ASD or LFD. First, it is based on probability, so you know more precisely the safety factor that is being applied in design. Because of this, it will encourage better designs. LRFD encourages the use of redundant configurations and the use of ductile materials. It also encourages the use of materials with low variability. Finally, it considers variability in construction and field conditions. Now let's look at some examples in bridge plans where we can see evidence of what was assumed in design. Looking at the front sheet of a bridge plan, there is a box in the upper right corner. This box contains basic data that was used in the design of the bridge. It gives the design code used, design methodology, live load assumed, other load allowances, and materials assumed. In some bigger bridge plans for more major structures, there are additional sheets in the plan which go into more detail on assumptions made for design and design criteria. Another thing we show on the plans of some bridges is a deck pour sequence. Deck pour sequence is important to the design of some bridges, in particular steel bridges. Pouring the deck at different times can affect stresses that get locked into the structure. It can also have an impact on the deck and amount of cracking that it might get if done out of the sequence shown in the plans. The amount of camber built into the steel girders is also based off the assumed deck pour sequence shown in the plans. Deviation from the deck pour sequence shown in the plans will impact camber. In some cases, this can be significant. So a proposed change in deck pour sequence may be required prior to fabrication of the girders. Construction sequences are also shown in the plan sometimes. The example shown here is for a segmental concrete box girder bridge. For this type of bridge, the construction sequence is critical because significant stresses get locked into the structure during construction and affect the time-dependent effects that happen to the bridge. Another example where a construction sequence may be shown in a plan is for steel girder erection. Deviations from the assumed construction sequence may be allowable, but they must be analyzed to ensure the design is still adequate under the proposed sequence. Other things to be looking for in the bridge plans are anywhere where it says minimum or maximum. Places where you might see this include in rebar details, steel details, and more. These dimensions are important to take note. In the case of minimums, these are listed in the plans for various reasons, including a minimum length of rebar needed to develop the bar for design forces, a minimum clearance needed for concrete to flow or for constructability concerns, a minimum area required for bearing, or more potential reasons. Maximum dimensions can be given for a variety of reasons as well. As an example, a maximum dimension may be given to ensure that the bridge is constructible and there are no interferences with other members. The final consideration that I want to emphasize is to follow the standard specs and special provisions for the project. Many items in the specs are there to ensure that the design criteria are met and to help reduce variability, materials, and construction. That I don't know if any questions came in.
Yeah, I don't see any questions came in on the chat box. Anybody have any questions? I can look at the attendee thing. Anybody have your hand up? So I don't see anything. Anybody? You can either do the raise your hand thing or type in the chat, but it doesn't look like any. Okay, Ben. Well, thanks a lot. Appreciate you sharing that information and your knowledge with us. So let's take, again, just to say a 5-minute break. We'll go till about 10:40 or so, 10:41, and we will get Ashley fired up. Okay. So Ben, if you want to answer this question. So question came in. It says, for the construction sequencing on the plan sheets, where does it say what comes first? So good question on that deck pour sequence that you were showing. I know you can answer that question.
Okay, well, I see it says construction sequencing, so I'll go off. I'll mention both. Construction sequence itself, it has it laid out step 1, step 2. So you just follow the steps. There might be staging 2 in some plans. They'll say stage 1, stage 2. So it shows pretty much and pretty clearly what order things need to be done. And there can be sub parts to each step. As far as deck pour sequence, let me share my screen here again if I can find my controllers. Well, I lost my screen, so I don't know what happened here, but if you look at the deck pour sequence, it'll have small numbers on the plan for each piece of deck that you'll pour. So the first piece that you'll want to pour has a 1 on it. The second part will have a 2 on it, and they'll also tell you if there's a certain direction that you're supposed to pour the deck. It'll have an arrow on it. So I hope that answers the question.
Yeah, the construction sequencing, like Ben mentioned. So oftentimes that's going to be one of the first few sheets. And, if you're doing stage construction and you're building half at a time, it'll show pretty clearly of what the sequence would be. So hopefully that answers the question. If it doesn't, you can type in. Again, Maggie, you can type in and we can try to explain via the chat box a little bit more. Okay, next up is Ashley Grozbowski. She's the East Metro Regional Bridge Construction Engineer in the bridge office. And she will be talking about foundation design. And Ben, sorry, I forgot to have you introduce yourself a little bit more, but Ashley, go ahead. You can introduce yourself a little bit more, and then you can teach us about bridge foundation design.
All right, so you can hear me?
Loud and clear, yep, sounds good.
Perfect. So my name is Ashley Grozbowski. I am the East Metro Bridge Construction Engineer, which means I typically support Anoka, Chisago, Dakota, Ramsey, and Washington County trunk highway bridges. And like Paul said, I'm going to be discussing foundations today. So what is a foundation? So the foundation is what transfers the load of the structure down into the ground, and there are several different types of foundations available. So the two most common types of foundations are pile-supported footings and spread footings. The third less common footing we use is called drilled shaft or caissons, and they're generally only used on our bigger bridges or depending on what types of soils we have. Spread footings are also known as shallow foundations and can be set on rock or on an excavated area of existing soils. And pile-supported footings are also known as deep foundations and are driven into the ground. Drilled shafts are also known as deep foundations. So we use spread footings about 8% of the time and piled footings about 90% of the time, and drilled shafts maybe about 2% of the time. But we have been using spread footings more and more, so I wouldn't be surprised if this number is a bit off. So the big question is, how do we determine which system to use? So let's start with some advantages of a spread footing. They're more economical. Spreads are approximately 40% cheaper when compared to a piled footing. If we can pour a little bit more concrete and not have to install any piling in that footing, it's going to cost us a lot less. The construction is much simpler than a piled footing. And I'll explain why that is here shortly. And because the construction is simpler, spread footings are therefore also much faster. And as previously mentioned, spread footings are considered shallow foundations, so they are typically close to the ground line, but still deep enough so that that bottom of that footing is below the frost line. So here you can see why construction is much faster. There have been examples where the contractor excavates to the bottom of the footing, sets the forms, they have a cage of rebar that they swing into place and poured that concrete all in the same exact day. So spread footings can really accelerate the work. However, there can be a lot more risks involved because spread footings are generally just sitting on the ground. We really don't want that footing of our bridge to move. So whether that's sliding from some lateral load or it's settlement from the soils condensing below, or it's undermining of the footing from a storm event in its final condition or during construction. So we need to make sure that we have solid ground under our spread footings. So during construction, make sure that you have the correct soils. Are you actually seeing what the plan stated you would see? And verify that that spread footing doesn't have any uneven settlement or movement of that footing. If the soil report says you're supposed to be seeing sand and you're seeing topsoil, clay, or peat, you're not going to want to continue. We might not be geotechnical engineers, but we do need to be able to identify when something has changed beyond what was called for in the plans. So does that bottom of the excavation look good? If not, use a hand auger to determine what it is that you have under the footing. And if you're not sure what you're looking at and have questions, ask your district soils engineer or the foundations unit or even your regional bridge construction engineer for guidance. So the primary reason for using spread footings besides economics can be figured out based on its name. A spread footing takes that load from the column and spreads it, the load out over a larger area of the soil, distributing all that dead load and live load from above down into the soil. The foundation of a spread footing is typically a larger area compared to a piled foundation. And so because of this, it spreads that weight of that structure over a larger area for greater stability. The other major foundation type is pile-supported footing. Piles are used when the underlying bearing soils are not adequate to support the loads for a spread footing. And most likely this has been identified in the plans, but if the plans include spread footings and the inspector notices some very weak soils, you must inform the bridge office for assistance and potential change of foundation type. So remember, a short delay now may save huge issues at a later date if significant settlement were to take place. Some advantages to a piled footing. As I mentioned, we use pile footings about 90% of the time. So most of our existing bridges are on piling, and we have had very little serviceability problems with them. Piling is used whenever the soils at and below the bottom of the footing are too weak or too compressible to provide a stable foundation for a spread footing. We have had less field risk with piled footings. They can be used in those areas of high risk with weak soils or where there is danger of erosion or scour, such as in streams. And piling provides us a much higher load capacity. So if we have a heavy bridge, we can have a smaller foundation by distributing that column load to strong piles. Some additional advantages of some deep foundations. If that bottom of that footing is scoured out, the piling still holds that footing in place, where if this were to happen to a spread footing, it would settle to that new ground line. If we have an extreme event, so for example, if a barge or an ice load were to hit this pier, that deep foundation is going to do a much better job of keeping that foundation in place rather than sliding that foundation. And for staging or future excavation, again, you don't have to be as concerned for disturbed ground around piling near the base of that footing as you do for accidentally excavating soil out from below a spread footing. So pile is generally a shaft of steel, concrete, or steel and concrete driven into the ground to transfer that structural load through weak soil to soil capable of supporting the bridge load. And keep in mind that the foundation support is very important, as the best built bridges on a poor foundation will have a shortened lifespan. In the interest of time, I'm only going to be discussing our two most common piles. The first one is called cast in place piling, and cast in place piles are driven as steel shells and then filled with concrete later. And they are the most common type of piling used on bridges at MnDOT, accounting for about 70% of piles driven. So it is important that after that pile has been driven, but before being filled with concrete, that pile is inspected for damage from driving. So here's an example of a damaged CIP pile, and it's because they just kept driving. So as that pile collapses, it takes a certain amount of energy to bend that piece of steel. And that energy will be used up bending the steel rather than sending that hammer back up. So you don't get near as much of a bounce back up. So when out in the field, watch for this. As that pile is collapsing, the hammer will only go back up a few feet. But then when it comes back down, it doesn't have enough energy to bend the pile. So then it bounces way back up. So you don't get that even pattern while driving. You get a short stroke followed by a long stroke. The second most common pile used in Minnesota is the H pile, and it accounts for about 25 to 30% of pile driven, and it is generally used for its toughness and its great strength. And H piles are better to drive through cobbles or rocky subgrade since they are not as prone to damage as a thinner wall CIP pile. So piling has two different types of functions that you'll see in the field. There is end bearing, and this is the pile we use when driving to a very dense layer or rock. And then we have what we call a friction pile, and this is a displacement type pile, and it's held in place by friction between the surrounding soil and the pile. So end bearing piles are piles where that tip of the pile is driven to bedrock or even a short distance into a hard or dense layer adequate to carry the design load without relying on friction. So almost any type of pile can be used in an end-bearing pile, but because of their high load carrying capacity and their penetrating relatively dense soil, the steel H pile is often selected. Cast in place piling can be used as an end bearing when they can reach that required tip elevation without concern of bending or buckling the pile or running into any rocks or boulders. So this diagram on the right shows that end bearing, or how the end bearing pile works. So as you can see, the majority of the resistance of the load, here's our load, is resisted at the tip of the pile with very little side friction resisting the load of the bridge. Friction piles are usually displacement, which obtain most of their load carrying capacity through friction between the soil and the skin of the pile. This load is called skin friction. So generally, friction piling develop lower pile load capacity since it doesn't have that end bearing resistance and it's just relying on friction. And it can be harder to predict the ultimate capacity of the pile because it's based on the surrounding soil. So the most common friction pile you'll see is the CIP pile, but the H pile is also sometimes used as a friction pile, especially when that soil boring indicates that there might be presence of rocks or boulders. So one thing to note during construction, especially in a cluster of piles in a footing, I keep using this word displacement as a description for this pile. So you have a larger amount of displacement of the surrounding soil when you drive a CIP pile. So when it's installed, it pushes that soil and increases the density of that soil, and it therefore makes it even harder to install the surrounding soils or piles. So if you have a lot of piles, you want to drive from the center of the piling out so that that displacement of the piles won't make it restrictive to driving those later piles. And then the diagram on the right shows how that friction piling works. As you can see, the majority of the resistance up to this load is on the edges of the pile rather than at the end. So this load on the side is larger, and then the load at the end of the pile is either zero or it's very minimal. So now we're going to go through a few miscellaneous topics related to foundations. The first is a quick readings of soil borings. In your bridge plans, usually at the back view pages of the plans, you'll see a sheet that looks like this, which includes the soil boring results taken. And they're taken as close as possible to where that substructures were expected to be located before the design even started. On the right is the soil classification type, letting you know that it's sand or clay. And on the left is the SPT N values, also known as your blow counts. So a super quick lesson on how that data is derived on the plans. How is that SPTN value, or rather the standard penetration test, N, which is the number of blows, determined in the borings? So a 140-pound hammer is dropped 30 inches, and the blow count is counted for that drill rod to advance 18 inches. The first 6 inches is discarded, and that next 12 inches count is what is recorded. So the N value is the recorded blow count needed to advance that drill 12-inch interval of soil. And the N value can then be correlated to help characterize the soil type. So this is a field log that is used to document all the findings in the field. Some of the soil descriptions might change during that lab soil classification. This boring log is the final product of the soil investigation that is used to determine the most suitable foundation type. So this is what we are expecting to see in the field. This boring log provides a little bit more information than what might be shown in the plan, but as you can see, it has the soil classification and the blow count information here. And it also has the water table level is also identified on this boring log. And that can determine, the expected ground line to know if we need dewatering measures or not. I did find this table in the MnDOT geotechnical manual online, and it can be used as guidance if you're new to this, to quickly determine based on the blow count ranges what types of soils you might have. So between 25 and 50, we're expecting a dense layer. So if we're here, we can tell with the 7 or 3 that we're in very loose or loose soils. So next, we're going to have a quick very quick lesson on soil types. It can be beneficial to have at least a minimal understanding of properties of different types of soils so that you can make sure that the soil under your spread footing is suitable for that type of foundation, or that your end-bearing pile isn't hung up in soft soils. So this picture is a generalization of soil types found in different parts of Minnesota. And this can be a starting point when looking at a project to see what types of soils might be encountered depending on where your project is located within the state. But this picture is even better for a quick reference. So we have our peats and our organic soils, which are usually dark brown or black and easily compressible because of how much water they hold. As you can see here, the moisture content is very large. But during the summer, they can become extremely dry and shrink. So they're not ideal to support foundations as they're unsuitable or unstable and should be removed before placing any foundation on it. Then we have our clays and our silts, which are fine grained sand and are also not ideal for foundation support because they also retain water well and can move that structure up and down. So for this type of material, we can mitigate this moisture by surcharging it or placing wick drains, which I'll explain what those are shortly, and that can help dissipate the water faster. And then we have sands, which are coarse-grained soils, and they drain water fast and can be compacted easily. So because of this, sand is an ideal foundation soil. Not pictured here, we can have loam, which is also an ideal soil type. Typically, that's a combination of sand, silt, and clay, and it maintains water at a balanced rate. And then, of course, we have rocks such as bedrock and limestone are very strong and are also good for supporting foundations as long as the rock is level. So if you have questions regarding soil types, you can check out the Geotech manual online, which I've got stated right here, or contact the foundations unit. So when a footing is to be placed on a recently constructed fill or of considerable height, you need to review the special provisions or plans as they may require a waiting period or surcharge due to settlement of these soils. There are 3 different types of settlement that, and the types of settlement depends on the types of soils. There are 3 different, the first is immediate compression. And this happens quickly and occurs mainly in sandy soils. You push down on it and it gets rid of all the air pockets, similar to a sponge. The second type of settlement is called primary consolidation. And this normally occurs in clays and takes longer than immediate compression because it's the result of water being squeezed out. So you can speed up that removal of water by installing wick drains, which again, I'll explain what that is in a second. And then lastly, we have secondary compression. And this is caused because of creep. And it usually takes several months to years for this to happen. So several years is a long time. So sometimes you need to add a preload or a surcharge to improve that weak compressible soil. So a preload is just adding the expected embankment fill to a height at or below the proposed ground line to that existing soil to induce settlement or consolidation of the foundation soils. So the preload is typically part of the permanent embankment that is just applied early. So you get that preload on there now so that those soils have time to condense and you're not having to wait as long. Where a surcharge is similar, but the fill and the weight are actually, they exceed what is required for final construction for additional load to push down on that soil. And then it's removed after settlement has leveled off. So contractors are constantly trying to decrease this window of waiting for settlement to occur, as it's a time where they can't really work in that area or work on that substructure. But listen to your geotech. If they tell you you need 3 months, you need to wait 3 months. Settlement plates are often required as part of the work, and the ability to continue working is dependent on those settlement readings before the contractor can proceed. So the length of the waiting period can be estimated by using laboratory test data, but the actual settlement occurring during embankment construction is then monitored with geotechnical instrumentation, such as settlement plates. So when the settlement with surcharge equals the settlement originally estimated, or that settlement has leveled off for the embankment, then the surcharge can be removed. So I've mentioned the phrase wick drains to help accelerate settlement. So a wick drain is a small tube drilled into the ground that acts as a conduit for water to flow out of the soil to the surface. So in this picture on the left, you can see the problem. We have a preload and the surcharge, but the soils drain really slowly down. But by adding these wick drains, you speed up that process for the water to drain just laterally, and then it goes up out to the surface, and then it will turn into runoff, and then it turns into runoff rather than just painfully, slowly pushing it down. So this graph just kind of shows us how a surcharge speeds up that settlement process by reducing that waiting period for the surcharge. So with surcharge, you can see here that settlement leveled off and the surcharge could be removed and the substructure could then start construction at this point. But without the surcharge, it took this much additional time for that settlement to occur and therefore pushed the construction this way back here. So our next miscellaneous topic is down drag. So what is down drag? Down drag is the settlement of soil after the piles have been driven, which then applies an additional load to that pile. The additional load is caused by that friction or adhesion between the pile and the downward moving soil. So here you can see we've got the tip resistance at the end bearing pile. You have your new fill, and then you have this blue area of condensing soil that is moving downward. And it's applying load to that pile, also pulling it downward. This load on these piles is called negative skin friction because it's acting in the opposite direction of this skin friction load. So drag load is the force on the pile caused by negative skin friction, and down drag is the actual settlement of that pile due to that drag load. So typically it's recommended that piling should be installed after the surcharging has occurred. So some methods for dealing with down drag: you could use a larger H pile section to increase factored structural resistance for piles. You could use more piles to reduce the applied load to these piles. Or you could reduce the soil settlement that occurred after pile driving by preloading or using wick drains, or both. So really the takeaway here is that you should understand what causes down drag and why we consider it in design. So sometimes a contractor wants to drive that piling, then start surcharging without considering the ramifications of it. So if you allow this and say the bridge plan doesn't have down drag, in the pile load tables, which I have placed here so you know what you're looking for, if it doesn't have this in your bridge plans, then it hasn't been accounted for. So you'd be adding load to that pile that we hadn't designed for. All right, so the next miscellaneous topic is pile setup. When a pile is driven into the ground, it disturbs and displaces the soil. So as the soil surrounding that pile recovers from the installation disturbance, a time-dependent increase in that pile capacity often occurs. So this is referred to as setup. You're displacing the soil by pushing this tube down it, and with sands, that soil kind of goes right back to where it was immediately. But with stiff clays, it can take a while before that soil kind of comes back and fills up all those voids around the pile. And with that time, that soil moves back and grabs onto that pile, and now we have that much more capacity, and then can hopefully meet that required bearing requirement. Piling is supposed to be continuously driven, But if the pile isn't meeting the bearing requirements, sometimes the project engineer or plans and specifications may require that contractor to redrive the test piles after a specified waiting period to determine the capacity that can be obtained by including pile setup. So there are many times where we need to rely on setup because that soil isn't strong enough to hold the pile. So maybe there's some stiff clays where we're anticipating a lot of setup. Typically, we will say to wait 24 hours, but sometimes it could be 7 days before you can start driving piling again in that area. We just had an example where after 24 hours with that redrive, we still weren't getting the required bearing capacity. So it was a Friday, decided to wait over the weekend, so roughly 72 hours. And when they redrove on Monday, they finally got that needed capacity. Just a quick lesson on what cofferdams and seals are. Cofferdams provide a watertight enclosure for the excavation and construction of foundations that are located below the water surface. So loose, water-saturated soils, water, or the need to protect adjacent work will indicate the need for a cofferdam. They're not super common, but they are the responsibility of the contractor since they're not a permanent part of the structure. But since our prime concern at all times is the safety of employees and of the public, it is advised to check the cofferdam plans that are submitted by the contractor. And do note that cofferdams must be removed to a specified limit after they have served their purpose. And this is what happens when you ask someone to review your PowerPoint for you. They insert pictures of seals. So I'm not talking about the singer or the animal, but I'm talking about the concrete seal that might be needed at the bottom of a cofferdam to seal the cofferdam before they start pumping water out of the cofferdam. So the seal has two purposes. It's to act as a barrier against inflow of saturated soils, inflow of water and saturated soils caused by the hydrostatic pressure of that water coming outside of the dam. And then they can act as a frame, so providing strength for this cofferdam. Concrete seals are specified in the plan when it is anticipated that a cofferdam cannot be safely dewatered to the bottom of the footing elevation. So this example sketch shows one situation where the seal is required. So plans will show which units require concrete seals and also the seal dimensions. And typically seals are larger on all sides than the footing dimensions so that there's extra room for construction. And the seal thickness will then depend on the depth of water above the bottom of the seal because a concrete seal is designed to resist that hydrostatic uplift with its mass. And then lastly, we have a drilled shaft. So a drilled shaft is a deep foundation that we don't see very often, but it's a cylindrical excavation in soil or rock that is then filled with reinforcement and concrete. So they are used when we have a bridge with very high load capacities. More common to see them for river crossing bridges as they can be constructed to depth below the predicted scour elevations, even in very dense soils or bedrocks. So these casings are sometimes pulled out, but they're there to act as a form for the rebar and concrete. Drilled shafts are commonly constructed by employing a rotary drilling equipment to drill the cylindrical hole. And then a rebar cage is inserted into that hole and then filled with concrete. So I know that was a lot of information really fast, but we wanted to touch base on a few common items that you might deal with in the field. So with that, are there any questions?
So again, it looks like nothing came in on the chat that I see. And I looked earlier if anybody had their hand raised. Scroll through again to see if anybody wants to talk. But does anybody have any questions for Ashley?
I have a question. This is Mark.
No.
Are the Packers going to win the Super Bowl next year?
Yes.
Sorry, Paul. You Packer backers. I don't know how we are with our mix of people here, but if we could come through the screen, we might. I just saw something. The only way to keep Tom Brady from getting another ring, have him dressed up in a Vikings uniform.
Mm-hmm. I saw that.
Okay, here did come a question, and we're gonna actually see this, but you can explain a little bit. The question comes in: what are some typical methods to determine the pile 10 count? So Ashley, you can address that. Andy, I know we'll be talking about that.
I don't know if I can. Do you know, Paul?
Yeah, I can address it. So
Yeah.
The pile 10 count. So Andy will be explaining this in more detail, but it's a great question. And when the pile drivers are driving, they're usually marking on the pile. As it goes down, they'll mark, and then there'll be 10 blows, and then they'll mark it again, and then they'll measure. And they'll say it's 2.5 inches, or it's 6 inches, or it's 1.25 inches, whatever. But typically it's physically marked on the pile. And then Andy's gonna, at least I'm assuming, Andy, that he probably can't talk because he's not in the panelist thing. But he will be going over at least some of the basics of how we use that 10 count. And there's cheat sheets. I'm sure he'll probably show something of the cheat sheets, that how the 10 blow count is used to know when we have capacity. And you're looking at the height of the fall of the hammer, so how much energy goes in, as well as then how stiff is that soil. So, obviously if your 10 blows are making it go down a foot, you don't have much capacity. But if 10 blows are making it go down an inch, you have a lot of capacity. And so how to determine it is typically in the field, marked like that. So, any other questions? Okay, a question came in: where in the proposal or plan is preloading requirement typically listed? So Ash, you want to address that one?
I believe that's actually in the Division S typically. So we might have a comment on our bridge plan that says to review the special provisions, and it's usually not actually located in the Division SB, but in Division S.
Yeah, and with the exception for abutment, oftentimes there will be a note on the abutment and often on the front sheet to include a 72-hour waiting period and something like that. But, so yeah, it's going to be in, if it's an abutment loading, it'll be often the front sheet and maybe on the abutment sheet. Good question. Anybody else? Okay, well, thanks much, Ashley. Great job. We are now at lunch break time. So let's break until 11:50. So just over a half hour. We will reconvene at 11:50. And next up on the agenda, I will be talking about structural components, and then that will be followed by plans and specs.